Okay, great. So today's topic is we're going to keep moving through our textbook, A Handbook of Statistical Analysis Using R, and today the chapter we're going to look at is the chapter on scatter plot smoothers and generalized additive models, okay? This Handbook of Statistical Analysis Using R, it does a fine job covering the topic, but I think I think it will be useful when, as the chapter will be a good reference for the future. But as far as learning the topic, I think this chapter from this other textbook called An Introduction to Statistical Learning, which I've made copies of and passed out for you, will be better. And so we'll be working through that chapter today. And so the chapter is, I have chapter 7. Chapter 7 from An Introduction to Statistical Learning. And actually, this textbook, Introduction to Statistical Learning, is available free as a PDF while you're connected to the UCLA library. You can go to Springer Link and just search for Introduction to Statistical Learning. And while you're connected to the UCLA network, you can download the book for free. Okay, when you go home, it won't let you do that, but I guess you can VPN in and then download it. Okay, so okay, just go to via Springer Link. Okay, and this entire chapter is, it's kind of like regression, except it is not it's not linear regression. Okay, and so the generalized additive model, and I'll just kind of show you where we are headed, and I have to talk about kind of the little pieces that get us there along the way. The generalized additive model, behaves a lot like regression, but it offers a lot of flexibility. Okay, so we can call them GAMs. Okay, the generalized additive model there's two parts that are very nice. Okay, it has a lot of flexibility. Okay, plus a decent amount of interpretability. Okay, whereas a lot of other modeling techniques that we have, you might have lots of flexibility, but then it's hard to understand exactly what's going on. So, we're not going to cover neural networks in this class, but with neural nets, you have a lot of flexibility and you can model a lot of things, but then what's exactly happening inside that neural net, it's hard to really understand what's going on. Linear regression, you have a lot of interpretability. term in your linear regression model, it comes with a coefficient, and it tells you kind of directly how much you expect that, changes in that particular variable to affect your model. And so you've got a lot of interpretability, but you're quite restricted to the kind of these linear relationships between things. Okay, and so what the generalized additive model is kind of like, it's similar to regression, except you can say component 1, or basically we can just say variable 1 and plus variable 2. Variable 1 maybe contributes kind of like this, and variable 2 contributes like this, and variable 3, maybe this contributes just like that. Okay, and so you can say each of these things contribute in kind of this additive way to the output, but none of these are restricted to either a directly linear or polynomial form. Okay, these all have kind of their own their own forms, and but you can still see like, oh, okay, variable 2, oh, okay, we can understand that it contributes almost linearly up to a certain point, and then once it reaches a certain point, variable 2 stops kind of adding onto whatever it is, the output that we're looking at, right? So maybe it's like, I don't know, money and happiness or something, right? Like maybe up to a certain point, more money makes you happy, but then after a certain point, it doesn't make your life any better, okay? Whereas, variable 3, this is gonna, every, as you increase it, it keeps adding to whatever it is that we're looking at, and, variable 1, it goes up, or, something like that, okay? So we get, because each of these are not limited to a straight linear relationship or anything like that, you get a lot of flexibility in that regard, okay? And then because you're kind of breaking them out into each individual variable, we can see we get an understanding of kind of how these things relate together. Okay, so in order to get there, we have to talk about kind of this idea of making smooth curves. Okay, so we have to cover smooth curves, and so smooth curves, we'll look at kind of regression splines, regression and smoothing splines, as well as local regression. Did you guys already cover local regression in your linear regression course? No.
Is that like Loess and stuff?
Yeah, it's kind of like Loess. A little bit. Okay. Okay. So local regression, yeah, it's we can Loess. Well, I mean, when you say a little bit, it's probably you're gonna get just a little bit today also. Okay.
I don't like it a lot, so that's cool.
Huh?
I'm not a huge fan of it.
You're not a huge fan of. I mean, it's basically. If you have a bunch of dots, it's like, say, eyeball a curve, and the Loess is just kind of a, without using to say eyeball the curve, you're having the computer eyeball the curve is basically, you're giving it an algorithm, a recipe for how to eyeball a curve is kind of.
What I have against it is that, like, on the spectrum of, like, explainability of the variance and, like, interpretability, it's just so far, it's, like, uninterpretable. In terms of, like,
you're not going to get a nice interpretable thing. You're basically just saying eyeball the curve, and this is the relationship that exists. Yeah. Right. A lot of these things, the trade-off for the flexibility and this is interpretability, right? Like linear regression, it's easy. You can say like, oh, the slope is 3, therefore if I add 1 to x, I expect my y to go up 3. That's a nice, that's nice, okay? Low S, yeah, there's no slope. There's just a line that you get to look at. Okay, so yeah, we'll so we can talk polynomial regression. I guess that's we'll cover that. So basically, polynomial regression. You know, you start off with linear regression, which you just have y is equal to your beta 0 plus your beta 1 x plus some error term, right? And then with polynomial, all you do is you just take polynomial variance of your x. So you go beta 0, and then you have beta 1x, and then you square your x, and you'll get beta 2x squared, and then you cube your x, so on and so forth, okay, until you get to, whoops, your dth polynomial term, and that's pretty much it, okay? And this is fine. It's just you know, too many terms can lead to, you know, overfit. Well, this is always a problem, right? Too many terms, you can overfit the data. And then, you know, the interpretability also decreases a little bit, and then at some point it's hard to understand what exactly, you know, if one of your terms is dollars, you know, what is dollars to the 4th power, or dollar, you know, what's a dollars raised to the 5th power, you know, that it's hard to it's hard to understand there. And then and that's what we have. And then the warning about extrapolating is especially important for polynomial regression, because as soon as you exit the range where you've collected data, the fitted lines tends to kind of shoot off into, you know, wild territories, right? So so, you know, if you've collected data something like this, okay, perhaps you can get your polynomial to fit this up to this point, okay? But then what happens outside of this range where you've collected? Chances are is you know, if you've done polynomial regression, chances are is this will probably shoot off kind of like that, and this will, you know, maybe shoot off like this, or if it's depending, it might shoot off like that, and these are probably going to be wildly inaccurate outside of this area where you've collected data, okay? And this is also going to, it should be reflected in the standard error. standard error of our estimates there. Okay. So, so we have another set of way to fit data, and that is the stepwise function. Okay, and so the stepwise function, it basically, you know, you have your data, whatever it is, and you're just going to say that for, you know, x in a certain boundary, okay, for, you know, x less than your first cut point, okay, C1 is your first cut point, you just say that you get, for x is less than this, you know y is equal to basically beta 0 plus beta 1, okay? And then for x between C1 and C2, you know, it's going to be y is equal to beta 0 plus beta 2, okay? So we're basically saying, so we say, I guess maybe my labeling is going to be a tiny bit off. You know, C1 of x is equal to the identity function that x is less than C1. I guess I've mislabeled this. Yeah, this will be C0. Okay. And so the identity function is basically 1 when it's true versus 0 when false. Okay. And C1 of x is going to be the identity when C1 is less than x is less than C2. Okay. So again, this is equal to 1 when this thing is true, and it's 0. So right here, if I call this cut 1 and I call this cut 2 and we call this cut 3, okay? In this span, C0 is true, C0 is equal to 1, okay? And over here, C0 is equal to 0, okay? And then I'll do a different color. So this will be C1 is equal to 0. Right here, in this span, C1 is true, all right, C1 is equal to 1, and elsewhere, C1 is equal to 0, okay? And then, and so basically we combine this linearly in, and we just say that y sub I is equal to beta 0 plus, and I guess this would be beta 0 times C0 of x, okay, plus beta 1 times C1 of x plus beta 2 of C2 of x, so on and so forth until you get to your last cut point plus epsilon. So I guess, so I apologize, this should be beta 0, and then this one should be beta 1. Okay, and so each of these things is equal to 1 only when this thing is true. Okay, and then so you get kind of these linear, something like that. Okay, you get a step function that looks something like that. So these are the, governed by these, indicator functions here. Okay. And so both of these, the stepwise function and our polynomial regression, this is both of these, the kind of the way that it's written out is based on the idea of a basis function. Okay. Which is what we're dealing with here. Okay. Okay. And so with basis functions is we have we have a set of functions, b1 of x, and b2 of x, and all the way through basis function k of x. Okay, and we're combining them together so that each value of y is some combination of the coefficient times the basis function of x. I guess these are x sub i's. Okay, and then so so for polynomial regression, our basis functions were base sub j, basis function j of x sub I was just x sub I raised to the jth power, right? So it was x to the first, x to the second, all the way up to x to the kth. So that was for polynomial function, polynomial regression. Okay, and then for stepwise regression, or stepwise functions, the basis functions were the identity, not the identity, the indicator functions for that particular set of cut points. Okay, so we said basis sub j of x sub I, this was the indicator function for is x in between that particular set of cut points. So we said c sub j is less than x sub I is less than the next cut point, right? So basis function is for when x is between is the indicator function. Indicator function for when x is between the cut points. Okay. And okay, and so these are kind of just some two examples of how you know, kind of the basis functions worked, and I think they're very easy to understand in this context. Okay, and so we are going to take a look at a regression spline. Okay, and a regression spline is kind of an expansion of the use of basis functions. Okay. Okay, so when we talk about regression splines, I think it makes sense to first begin with kind of this idea of piecewise polynomials. Okay, so you know, first so you can imagine imagine fitting a bunch of piecewise cubic polynomials. All right, so we will fit a bunch of piecewise cubic polynomials. Okay, so each cubic function is you know, beta 0 plus beta 1 xi plus beta 2 xi squared plus beta 3 xi cubed plus epsilon. So we'll say this is y sub I. Okay, and then we're going to combine this kind of with, so you know, we're taking kind of the polynomial regression, and then we're going to kind of combine it with our stepwise with the kind of the cut points. Okay, and our cut points, we're going to call these we're going to call them knots. Okay, and so the knot is the spot where our beta coefficients change. Okay, so we're going to have so we you know, kind of we're combining the idea with you know, a knot is a location where these beta coefficients change. Okay, all right, so let's say just if we have a single knot, okay, with just one knot at location C, then we get kind of what the book provides on that page 271. You have we're gonna have two equations: beta 0 1 plus beta 1 1. I'm gonna just do beta 1 1 x, beta 2 1 x squared plus beta 3 1 x cubed plus the epsilon, and this is for if x is less than c. Okay, and then we have beta 1 2 x plus beta 2 2 x squared plus beta 3 2 x cubed plus epsilon if x is greater than c. Okay, so this is all we're doing. We're using the same x's. Okay, it's just that our beta coefficients change at the point when x crosses that knot C. Okay. Now, now if we fit our data to this, okay, you can end up you're basically just drawing a line at C, and then you're basically fitting a cubic polynomial over here, and then it's like you've got different data over here, and you're fitting a cubic polynomial over here. Kind of that's kind of how it goes. All right, and so there's kind of this question of you know, how many knots should we put? Okay, and you're gonna basically, however many knots you're gonna have one more cubic thing to fit, right? So if you have with 1 knot you've got 2 cubics to fit. With 2 knots you're gonna have 3, and with 10 cubics you would have 10 knots you'd have 11 things to fit. Okay, and then if you fit this, you can end up getting discontinuous things, right? I mean, just if it's piecewise, right? Let's say we have some. Let's say we have something like this, okay? And we want to fit a function. So I don't know. Let's say I draw this here. So now I'm going to try to fit a cubic. I don't know what a cubic function would look like. Something like this, maybe. Okay, and then maybe over here, something that looks like this. Okay, and this is our knot. And so we can try to. So we get, this is piecewise cubic, all right, and you can end up getting discontinuous functions, right? So with piecewise polynomial regression, you can get discontinuous functions, all right, and which is undesirable. To say the least. Okay. Okay, and so we can start to throw in some constraints here, okay? And we can say, okay, well, you have to, they have to join, right? Okay, so we have some constraints. Okay, so we can say, well, the cubics must be continuous. Okay, and that can happen. All right, let's just making up my data again. Okay, and you can get something that looks like this. Okay. And this point still looks, they're touching now, but this still feels, it's not smooth, right? Okay, so to force smoothness, okay, to make sure things are smooth, we can add another constraint, and that is that the first derivatives have to be the same, and the second derivatives also have to be the same, equal to each other. So just their points and the derivatives have to be continuous at that knot. Okay, And so the first derivative will make sure they have this slope, and the second derivative will make sure they have kind of the same that same curvature there. Okay. So we add additional constraints. Okay, and we make sure that the values, the first and second derivatives, are all continuous. At the knot. Okay, and then when you do that, then you'll get a nice smooth, you'll get smooth at the whatever whatever it is that you're looking for. Okay. And so okay, and so how does this work in terms of the mathematics? Okay, is we can express the this thing, how can we make sure the first and second, we can express this using some basis functions here. Okay. Okay, so if we have with k knots, okay, so a cubic spline with k knots, can be modeled okay, so this is just kind of our regular old basis function, okay? Beta 2 to, oops, our second basis function. Okay, and then we model it up to, if you've got k knots and it's a cubic, then you're going to have k plus 3 basis functions, okay? And we add what we call a truncated power basis function for each knot. Okay, so we we start off with a cubic polynomial, okay, and then we add a truncated power basis for each knot. Okay, so basically we cubic polynomial as bases, okay? And then we add a truncated power basis function per knot. Okay, so how is this? Okay, so the truncated basis function is basically you have starting at it's a function of x, and basically our cut point, it's a xi. This is a xi. and we write it like this, and it looks kind of funny. Okay, this little plus here means that this only exists for when x is greater. So it means that it's exactly this thing for when if x is greater than xi and it's 0 otherwise. Okay, so the plus just means it's this when this is greater than 0, basically. Okay. The plus means we only worry about it to the right of xi. Okay. Okay, and so when you do this, okay, adding something like this to a cubic polynomial, when you take the first or second derivatives at that spot xi, okay, it doesn't affect it, right? So if we add this, okay, so using this kind of basis function, like this will not affect the first and second derivatives at the point x equal to xi. Okay, and so this is how we get away with increasing the complexity of our model without messing up the first and second derivatives, making sure that they stay continuous. Okay, so this is how we can guarantee our regression spline remains smooth. Okay, and then and we have another thing called a natural spline. Okay, and so this is when you when you fit this, you can get a high amount of variance, and there's a good picture of this on page 274 in your handout. Maybe I can pull it up here. Okay, the variance just increases can increase quite a bit, and so there's a natural spline that it comes with additional constraints on the function itself, and that is it has to be linear at the boundary. Okay, so so it's down in this point, and so I don't know if you guys can maybe not in your. This part basically says this part has to be linear and not a cubic, okay? And then over here at the boundary spot, it's got to be linear and not cubic, okay? So it kind of reduces the variation that can happen at the end, right? Because otherwise you can have these things that shoot off, okay? So that would be called a natural spline. To kind of reduce some of the variance that we might see. Okay. Well, you can just kind of highlight that. I know on your black and white copy, just say it's hard to see, but on your black and white copy, the natural cubic one, because they look exactly the same. It's a straight line here. Versus the regular old cubic can be curved. Okay, so this is a straight line. All right. Okay, and then this is always a question that is difficult to answer. Is how many knots should you have, and where should you put the knots? Okay, and it's a hard question to answer. So we can. So trying out the different number of knots, you can kind of you can do some kind of some cross validation to decide what number of knots would give you the best performance. Okay, and yeah, it's a tough thing to do. Okay, so so that's a regression spline. Okay, a related but slightly different is the smoothing spline. Okay, so let's cover that here. Okay. So we have the regression spline, and now we'll talk about the smoothing spline. Okay, and so. So with a smoothing spline, okay, is we're going to try to minimize the residual sum of squares, right? Okay, so just in terms of fitting, if we want to have a function that fits our data, okay. We can try to approach, or try to minimize the RSS, our sum of squares residuals. Okay, and so we can just say, which is the difference between the actual value and our predicted value based on our x, okay? Okay, and if we if we gave our function g basically unlimited freedom here, okay, then what this would do is it would fit all the data as much as possible. It would be as wiggly as possible to make sure that RSS is as small as possible, right? So if g is unbounded, okay, g of x has no constraints, like we're not doing polynomial regression, or we're just saying g of x, you be whatever you want to be, okay? Has no constraints on it. Okay, the way it will minimize your the RSS will be to just fit all of the data perfectly. Okay. Will be to try to fit all the data perfectly. Okay, and we know that that's not going to be a good good solution either. So so what do? We introduce kind of like a penalty for being not smooth. Okay, so we say, okay, if you're gonna play it that way, we're gonna put in a penalty if you're not going to be smooth. So kind of the measure that we can use for how smooth something is the second derivative, right? So the first derivative is your slope, and then the second derivative is how often that slope changes, or how much that slope changes. So the second derivative can be used as a measure of how quote rough the curve is. Okay. So we use this as a penalty for not being smooth. Okay, and so what we say is what we now want you to do is minimize a combination of the residual sum of squares, okay, plus, and we're going to take the second derivative, and we integrate the second derivative across all of our values. Okay, so we integrate kind of how rough the function is across all the points. Okay, and so this is kind of our roughness. Okay, and then this is your RSS. Okay, so we want to minimize the sum of squares at the same time as minimizing the roughness. Okay, and how much weight we give the roughness in comparison to the RSS, that is controlled by lambda. Okay, so we choose lambda to kind of balance how important this roughness is versus the sum of squares, residual sum of squares. Okay, so we choose lambda to balance how important the smoothness is in comparison to RSS. let's see if we have some pictures for this. I don't know how many pictures of this, but basically, this part really big. I'm gonna just. We may have. Right. So if you just kind of gave the function g kind of some unlimited fit, it would try to fit everything as much as possible. Okay. And obviously we don't want that. Okay. And with some amount you can kind of try to fit this, or if you crank it up too high, then it will force something where it really resists changes in the slope. Okay. So this, the red would be probably lambda is equal to 0, and then this is like quote good, and then I don't know exactly what these values would be, and then this would be too high. Okay. And so this is kind of just kind of a overview idea of the smoothing spline. Okay, and then there's some discussion in the text about choosing that smoothing parameter. Okay, smoothing parameter lambda there. Okay, let's see, and I guess they used to try to determine what value of lambda. They've done some leave out one cross validation error to do this and see how it fits. But okay. All right. Okay, and then so that's those are some spline ideas. Okay, ideas for fitting splines. Okay, and then and here let's talk about local regression. Okay, and so this is kind of your low S or your low S, and I'm still not. I don't know entirely. You see it both written both ways, and to be honest, there's like low S, and then there's low S with a W, and I know that there's like a difference, but to be honest, I don't really know what the difference is there. If I ever have to do low S, I just type in on R, do low S for me, and but these are both local regression. Okay. Okay, and really, it's local regression is pretty much it's like you're giving a recipe on how to eyeball a smooth curve through the data. Okay, it's kind of you can think of it as that way, right? You can think of it as it's kind of similar to a running mean. Okay, so similar in concept to having a running mean. The way a running mean works is, you have some data here, right? and basically, I'm going off a little bit off the text here. If you're wondering, why this doesn't match what you're looking at. And basically, the running mean is like you at some point x here. Okay. Yeah, sorry. This is supposed to line up. Okay. You go. I'm gonna go. Maybe 2 values. Why am I having such a hard time? 2 values below and 2 values above. Okay. And then you say, okay, well, at these 5 data points, the mean value for these 5 data points is right here, okay? Okay, and then you go to your next data point right here, okay? And then you say, okay, well, I'm going to look at 2 points below and 2 points above, and you go, oh, okay, well, with these 5 data points, maybe the mean is right there, or something like that, okay? And then so with the running mean is you've got like this window that includes a few data points above it and a few data points below each x, and you're calculating the mean of those things, okay? Kind of like that, right? So for each x, you look at a quote window of values that include some values of x above and values of x below. Okay, and then you just kind of you take the mean of those. Values. Okay, and with local regression, things similar, except you're not just taking the mean. You're weighting them. Okay, so you weight those closest to your value of x to be high, and you weight the values kind of at the fringe of your window to be low. Okay, for local regression. Okay, you weight the values near your x to be high, and values far from x are weighted lower. Okay, and then you basically are fitting a weighted regression model to weighted least squares model to that kind of that window of data. Okay, and so you fit and basically you get these nice. It results in kind of these nice, smoothish curves. Although with local regression, you don't really get a function. Okay, you don't have like y is equal to some combination of your x's. It's just for this x, our prediction for y is this value, and for this x, our prediction for y is this value, and for this x, our prediction for y is this value. And the way we calculated this value is we did this locally weighted thing. Okay, so that's the disadvantage. Okay, disadvantage is there's no functional form. Of, y of x. Okay, just, for this x, y hat is equal to, this value, okay? And for that x, it's something else. But you get a curve, right? And so you're essentially just here's a plot of points, and try to draw a smooth line that fits the data, okay? And it gives you a recipe for doing that, depending on how you want to weight the things. Okay, let's take a look at some of this stuff here before we look at the generalized additive models. We'll take a look at how some of this stuff works in R. I tried to type up as much of the code from this thing into, or tried to at least like copy and paste it, but when you copy and paste from a PDF, it always gets a little bit jacked up. And let's see, that's from the other. Okay, so we're going to take a look. I'm skipping ahead. So in the text, I'm going to go to the lab part 7.8, and then we'll come back to 7.7 later. Okay, so we're going to take a look at the wage data. Okay, and we'll do this in R here. Okay, so throughout the text, we've been trying to fit how wage, the wages that someone might earn is it related to their age, okay? And obviously this is the wages that someone earns is a lot of things go into it, but yeah, age is probably is a factor that goes into it. And so here it is. Here, let me I don't know if a couple of you have your computer, so I'll upload this onto CCLE. If in case you want to follow along, you don't have to. But let me do this for you. I might need to make some corrections to it later also. Okay, and so if you okay, so if you download this from R, from CCLE, you'll probably need to install a few libraries in order to get it to work. ISLR is the library associated with this other textbook, the Introduction to Statistical Learning. A great textbook, by the way, if you want to take a look at it on your own time, in all the free time that you guys have. Joking. All right. Okay. And so that's ISLR. We'll attach the wage data set here. Okay. And so let me just show you kind of what. Well, here's this function poly. Okay. Poly age. All right. And here, let me just show you what 1 through 10 does. So if I do poly of 1 through 10, comma 4, and then let me do raw equals true. Okay, what this does is are you guys able to see this? Here, I'll rearrange my panels here. Console on the right. Okay, we'll do this. Okay, so polynomial 1 through 10, it just says, okay, here you got 1 through 10, and then the second one is they squared it. So it's, the 1, 4, 9, 16, 25, and then the 3, you cube them, and then to the 4th power, you raise everything to the 4th power, okay? And that's if you do raw equals true, all right? If you leave off raw equals true, which is kind of its default behavior, is that it does all of this funny stuff, and you're like, what's going on here? What it does is it basically does the same kind of thing here, except you get what they call orthogonal, I don't know what you call them, orthogonal vectors, okay? And but effectively, the kind of the relationship between the linear, quadratic, cubic, and I don't know, quartic relationship remains there. Okay, so this is what we have. Yeah, question.
Is that like similar to centering, or is that different?
It's a little different. Let's see. Let me ask. What? Polly, answer me questions. Okay. Compute orthogonal polynomials. These are orthogonal to the constant polynomial of degree 0. Alternatively, let's see. The orthogonal polynomial is summarized by the coefficients. Let me see. I think what happens, it's not centering, but I think if I did, so let me do poly 1, okay, so poly 1 colon 10, let me just do of 2, and let me, if I do the correlation here, I think, yeah, so when they're orthogonal, the correlation is 0 between them. Okay.
So it's the same. So it's kind of doing some. It's for the same reason, but it's not the same thing.
Yeah, it's a little bit different. So yeah, but so whereas if I did raw equals true, then you're going to have high correlation between between the linear and the thing. So yeah. Yeah, I think that the kind of they do end up getting centered, but like it's not just we're not just scaling and recentering them, because we can see with the 4th power, it goes positive and then negative and then positive and negative and positive, so it forces like a correlation of 0 between these things. But I don't know how it calculates these things out. Yeah, no, it's a good question. I don't know how the underworkings of the polynomial function. But like raw equals true, that's easy to understand. The orthogonal thing, it does something. Okay, and so we can do a linear fit. This is just linear regression here. Okay, and it says this is what it figures out to be the thing here, and maybe I can plot wage as a function of age. No, shoot. Of course. Okay, and so we have this, and then can I plot the fit on here? This is what we get. let's see. No. Okay. Okay, and then if we did the raw, then we get something a little bit different. Okay. You know, but as far as, oh, something crazy happened here.
That doesn't look great.
I think I messed something up there. You know, yeah, and then we have a few options. You know, listed in the textbook. We can do. See the way R uses the I function. It's a little bit different, but so here this is just a polynomial regression here. Okay. All right. If we take a look at age limits, we can see, okay, the youngest we have recorded is 18 and the oldest is 80. Okay, and then so I'm going to just create what we call the age grid, and all this is just the values 18, 19, 20 through 80, and we're going to create kind of some predictions based on our fit. Okay, so we can say, you know, what did you predict for, you know, what is your predicted wage for 18, for 19, for 20, all the way up through 80, except they're offset by 17 here. Okay, so we can do predictions, and then we can create kind of some confidence intervals by just taking our predicted fit and adding 2 standard errors and subtracting 2 standard errors. Okay, because R's predict function takes into account the standard errors of all of our things. So let me just okay, and so here we get, it's hard to see with all of these things, but we get kind of our confidence interval bands of our predicted wages for all of these different things. Okay, and then so the textbook just provides some code for you know, plotting some of this stuff. Okay, so you know, we can plot this, and we'll add the prediction line here. Okay, I guess this is the 4th degree polynomial fit, and then we can add kind of it's hard to see, but this is kind of the bands showing our upper and lower bounds of what we predict this to be. Oops, shoot, what did I do? Not of the figure margins too large. It's always it's the bane of my existence here. Okay, and then we can also create you know, other age and SE bands. Okay, and then we can see. All right, what about what if we used the, well, what did I do here? Do try catch. Incomplete. No, that's fine. Okay, so here we can see, so here this is, we're just comparing the 2 different fits. One was using the orthogonal polynomial regression, and one is using the raw, where I took age and I kind of just squared them, cubed them, and raised them to the 4th power. And we can and basically we just asked R, okay, make your predictions for the second model. Okay, so this first one was based off of the orthogonal things, and then the second one was based off of just the raw raising to the raw whatever. And we can see, you know, what is the difference, okay, predictions of the using the orthogonal versus the raw scores, okay, and what was the biggest absolute value difference that we saw, and it's on the order of 10 to the minus 11, okay. So using, whether you're using poly comma raw, which I think is easier to understand, versus kind of the orthogonal polynomials, it doesn't really make a huge difference as far as the model that gets fit. Even though our coefficients end up being different and things like that, doesn't make a huge difference. So in that regard, if using raw equals true is easier to understand, then you can go ahead and use that. The problem though is, you know, you probably learned in linear regression, in your linear regression course, is that when you have high collinearity, the coefficient estimates are a lot more volatile, right? Okay, and so that problem doesn't go away, and so that's kind of generally why when you do polynomial, I think a lot of times they use this orthogonal thing where you don't have to worry about that collinearity aspect, but the trade-off is now you have these orthogonal vectors that you don't know what to do with, right? You know, it's hard to fully understand what the 4th order orthogonal thing on age is, okay? Other than to say, well, it's kind of related to age raised to the 4th power, which I don't even know what that means either, okay? But, you know, I think it's okay to say, like, oh, you know, I fit a polynomial thing, and then people will kind of just say, like, okay, I kind of understand what you're trying to do. Like, we understand, we're, like, accustomed to seeing polynomials, but then if you ask me, like, oh, if you added 1 to the age, you know, 4th order, you know, age raised to the 4th power, I don't, on a practical setting, I have no idea what that means. Okay. Okay, what did I do? All right, so here we are. Okay, so anyway, this to show that not that big of a deal. All right, we can do some ANOVA analysis to see, you know, how much of a difference does it make fitting linear. So I'm going to call fit 1, fit 2 is going to be quadratic, fit 3 will be cubic, fit 4 is whatever, to the 4th power, and fit 5 is to the 5th power. What are the names once it goes past cubic? Tetra? Quartic?
Antagonistic.
I believe you. Okay. All right, and then so we just run, you know, we say ANOVA between all of these fits, right? And then we say, okay, well, what's the difference here? And so, okay, well, quadratic seems to do better, and then cubic, okay, sure, but then, you know, adding a 4th degree, maybe your gains are not as great, and then adding a 5th degree, you know, there's definitely some diminishing returns, right? As far as the kinds of gains that we get from adding these things. Okay. So either, so based on this, we would just say, well, okay, cubic or okay, the textbook says quartic polynomial, but lower or higher order models are not justified. Okay. And then, okay, and it says, and in this case, instead of using the ANOVA function, we could have obtained these p-values more succinctly by exploiting the fact that poly creates orthogonal polynomials, okay? And if we looked at the orthogonal polynomials here, and we just did, because we said poly h5, this creates orthogonal polynomials of degree 5, we can do coefficients on this, and we look at kind of the p-values. We see these p-values are all significant, and then this one is not, right? And that these are actually these p-values all correspond here because they're all kind of orthogonal to each other. Yeah.
Cool side note, apparently anything after the fourth power can be called x tesseracted to the fourth.
X tesseracted.
Yeah, which seems kinda crazy.
That sounds really cool. That's like and whenever I hear tesseract, it's like
It's a one movie.
A Wrinkle in Time, or
Wrinkle in Time, that's-
A Wrinkle in Time
that's
from my Madeline Angle. Yeah, exactly. A Wrinkle in Time. So, did they make a movie?
There's a what?
Or there's a Marvel?
They made like a
Yeah.
Hallmark movie.
Oh, a Hallmark.
It
Oh.
was pretty cheesy.
Okay, well
Sure.
that's disappointing. Because that was an awesome book as like a 6th or 7th grader that you're reading. I don't know when you're supposed to read this textbook. All of the international students, you should check out these. Did you ever read A Wrinkle in Time? Okay, add it to your recommended reading, young adult literature. Okay. All right. What am I doing here? Oh, polynomial regression. Okay. And all right. Okay. Yeah. So the ANOVA method would work whether or not we used orthogonal polynomials, and then we could add other terms to the fit as well. Okay. We could have applied if we wanted to look at whether or not does somebody make over $250,000 per year. Okay, like R does some pretty cool stuff. You can use the I as the indicator function here for is wage greater than 250. Okay, so then it turns the true false from wage, is that greater than 250 or not, into a 1 or 0, and now you can fit logistic regression, right? And then so you can do fit GLM, poly H4, data is equal to wage, family binomial, and then maybe we can do a summary of this fit, and then we see, okay, age is significant, and all of this, and all of this, and we can make predictions based on that for that relationship there. Okay, I'm going to skip ahead to the section on splines. Okay. We could look at all of this stuff, but let's go to library splines here. Oh, shoot, we're gonna run out of time. Okay. Okay. So in order to, so we got to load up library splines. Okay. And you might need to install that. Okay. Is it okay?
Yeah.
Okay. Yeah. And and we use the function BS for basis splines. That's exactly what it stands for. And then we say, okay, well, we're going to make basis splines for the variable age, and we're going to create knots at 25, 40, and 60. Okay, this will do it. Okay, and so we say, okay, here, let me just kind of show you. So BS is for B-spline basis, okay, and okay, and then so we'll fit the linear model, fit a linear model between wage and after we've created the splines for age, okay, and then we'll run a fit. We'll fit. I'm sorry. We'll create our predictions. Okay, and so these are the predictions for all of these different ages again. Okay, and so let me we'll create our plot here. Let's make this bigger. Okay, and so this is what we have for after fitting our basis splines here. So this is we fit kind of the BS. The default for basis splines is cubic. Okay, and so here it's kind of fit at 25 and what did I forget, 40 and 60. It's fit different things here. Okay, and we can add kind of our upper and lower bounds. Oops, something. Oh, I have to get rid of the leading and trailing space here. Okay, and so we can kind of see how our function works here. And if we look at just some things about the basis spline thing itself, okay? So if I look at the dimensions, just kind of exploring the properties of this basis spline function, it produces 3,000 and 6 dimensions here. We can kind of just take a look. Let's look at the dimension of wages. Oops. Okay, so it's giving us kind of 1 for every x that we get. Okay, and then let me just kind of show you the head. Well, let me look at head of wage $sign. Oops, never mind. Okay, so these are kind of our first 6 ages right there. Let me just show you the head here. It's, so let's see. For our how is this working? Our cut points were at 25, 40, and 60, and so how do I explain the different values we're seeing here? I have 3,000 for the oh shoot, I don't remember. So for 18, this is well into the kind of the small area, and so the basis spline there is going to be 0 for all of them. And then you can kind of see for 45, 43, and 50 and 54, these 4 values here, they all get values here, and I'm just trying to, and the 24, which I would think is on the smaller side of the 25 and 40, well, somehow it's getting values across both of these, but okay. Oh, I guess, let me see. If we ask where, sorry. No, not the notes here. If I ask, if we specify the degrees of freedom in R and ask for where it places the knots, it puts them at these 3 locations. We can ask where it puts the knots here, and it'll put the knots at where we specified them. I'm sure of it, but I'll just double check. No, not dim. Yeah. Okay. Well, I'm not entirely sure how this how the basis splines function itself works, but it kind of creates a matrix of the values against which you know, each observation gets its kind of zeros and its kind of weighting of some cubic function here. Okay. All right, and okay, so we can plot. We can use instead of BS, we can use NS for natural splines. Okay, and so this is another fitted value. We can say have 4 degrees of freedom. We'll create another set of predictions. Okay, and then over here into our plot, which we have, we'll add this, a red line for and maybe we can tell the difference or not. Basically, with the natural spline, it forces that last portion over 60 and before 25 to be linear. Okay, and so we can see this ends up being a straight line right here in kind of its last section right there. And again, we could specify the knots ourselves, or I guess in this case, because we just used NS and we didn't specify the knots, R probably did it for us, or R did it for us, and we can ask, you know, what are the attributes on this, and okay, and okay, so the last knot I put at 51, so it just puts them at the kind of the 3 at our percentile breaks here. Okay, and let's see. So that's natural splines, and let's see if there's anything else. Oh, smoothing splines. Okay. And then so for one more, we'll do we'll create smoothing splines. All right, and then so there's a function for smoothing splines, and we'll fit this. Okay. So this is using df is equal to 16 as kind of one way to declare how smooth this thing has to be. So again, smoothing splines is the you're trying to minimize the sum of squares residuals, but and the way you control that is with this this parameter that explains how much penalty it gets for being curvy. And I think degrees of freedom here allows it more flexibility, and lower degrees of freedom gives it less curviness. Okay, and so over here with smoothing spline we use CV equals true. CV equals true means use cross validation to try to determine how many degrees of freedom to use. Okay, and so is used for the smoothing parameter. So if you look up smooth spline, okay, that's what we have here. And so I'll do that fit 2, and this plot we will put in blue. Okay, and so maybe we can see the difference here. And so if we look at the red is a little bit more wiggly, and the blue is smoother in as far as smoothing splines go, and it has fewer degrees of freedom if we look at that. Okay. All right, and then the last one is local regression. Okay, and local regression here we just use low s. Okay, and with low s you get to choose how big of a window you want in terms of how many of the things. So usually your bigger window will take into more data on the side, so you get kind of a smoother thing. Smaller window, you're going to get a little bit more wiggle. Okay, so we got fit 1 and fit 2, and we'll plot this. And again, the red line is the one with the smaller window, so that's going to get more wiggly, and then the blue line has the wider window, so that's going to get more